Thank you. Just one question. Will one of you be monitoring the chat? Because I'm not able to see it on the screen. So if you can monitor the chat and interrupt, that would be great.
Okay, good.
Okay.
I will look at the chat.
Yeah, thank you so much. Okay, thank you everyone for coming to my talk. Today I'm going to talk about a precise high-dimensional asymptotic theory for AdaBoost. This is based on joint work with Tengguan Liang, who is currently an assistant professor at UChicago. Okay, so the rough outline of my talk will be, I'll start with describing the AdaBoost algorithm. It's a very, very classical algorithm and it's, it was introduced around 95, 96. And I'll review some of the classical works in this area, but this area is very rich. So I'll try my best to review the works most related to our work, and I'll just give pointers to all the other threads in the literature, but it will be more focusing on related works, the closest to what we did. And then I'll go into describing our contributions. So broadly, our contributions can be sort of categorized along two veins. So one vein of our contribution is a precise analysis of the AdaBoost algorithm itself in a high-dimensional setting. And the other vein is the following. So it turns out that the AdaBoost algorithm is the solution to that algorithm is related to things known as the min L1 norm interpolant and the max L1 margin. So the other vein of our contributions comprises precise study of these margins and interpolants. Then towards the end of this time, I might introduce a new class of boosting algorithms and similar to AdaBoost, where similar results can go through and then close with takeaways. So that's sort of the broad outline. Okay, so let's get into boosting and then specifically AdaBoost. So what is boosting? By now, boosting has come to mean, it's a very general term. Roughly what it means is the following. So it's a problem of producing a very accurate prediction rule by combining rough and moderately inaccurate rules of thumb. So what does that mean? So what boosting does is it's an iterative procedure, and at each iteration, it basically trains a weak learner. What it means is it tries to produce a classification. Let's restrict to a classification problem for this talk. Then it tries to produce a classifier that is a little bit better than random guessing. Okay, so it's not a great classifier. So it's only a little bit better than random guessing. But then over the course of iterations, it continues to produce such classifiers. And then when it stops, it aggregates these classifiers in a very smart way. And turns out that this aggregated classifier produces a very accurate prediction rule, or a very accurate classifier. So the classifiers at each iteration, which are just better than random guessing, those are called weak learners. And then when you aggregate and produce a really good classifier, that's your strong learner. All right, so boosting is a very old subject. Its roots trace back to the works of Valiant in computational learning theory, and probably the earliest boosting algorithms were independently created by Shapiro and Freund. But the major breakthrough that occurred in this literature is the AdaBoost algorithm that is due to Freund and Shapiro. So let me maybe spend a few minutes to describe the algorithm. So this is almost a rewrite from the Freund and Shapiro original paper. So it's a bit notation heavy. Let me try to explain in words what it does. So suppose our training data is denoted as follows. So I have xi's, which are the features in some RP. And for this talk, I'm going to restrict to binary classification settings. So I'm going to just represent yi's to be plus or minus ones. So what AdaBoost does is it's an iterative algorithm. At each iteration, it maintains a set of weights on your training data examples. So what it will do is it will start with a bunch of data weights. So eta naught is the starting weight, and usually people start with uniform weights on your data points. Okay. And then what it does is the following. So let's look at the steps. So let's fix the time t. At the beginning, what you're going to do is, with respect to the 0-1 loss, you're going to look at the weighted training error, and you're going to try to find the direction that minimizes the weighted training error. Okay, so that's what this step does. This VT plus 1 is trying to find which direction minimizes the weighted training error. All right, so eta ti is the weight at time t on example I. All right, so now suppose you know this direction, then you're going to do two things. One, the goal is if this is a good direction, you want to take sort of a large step in that direction. And if this is a bad direction, you want to take a small step in that direction. And the other thing is, based on how much error you are incurring at this iteration, you want to update the weights on your training examples for the next iteration. Okay, now AdaBoost does something very clever. So what it tries to do is it calculates this step size alpha t. So if you look at this, this is inversely proportional to your weighted training error. So VT plus 1 is this direction. So if you looked at this particular classifier, VT plus 1, this is basically the weighted training error you will incur for this particular classifier. So alpha t is inversely proportional to that error. Okay, so the error that VT plus 1 will incur given these weights. So now what AdaBoost does is for at this step, it's going to move in this direction VT plus 1 proportional to a magnitude given by alpha t. So because alpha t is inversely proportional to the error, so if their error is low, you're going to move a lot in this direction. If the error is large, you're going to move only a little in this direction. So that's the coordinate update. So theta t is the iterates you're maintaining. So that's what it does here. And then it needs to update the weights themselves for the next iteration. So what it does is it takes the weights at this iteration. For each example, it basically calculates, how bad or good VT plus 1 is as a classifier for that particular example. But because of this exponential negative weighting, it basically, what it does is if VT plus 1 classifies an example very well, it downweighs that example for the next iteration. Okay. And if VT plus 1 classifies an example poorly, it upweighs that example for the next iteration. So basically, the essence of the algorithm is each time you're maintaining a set of weights, you're trying to find the best possible direction. And if the direction is good for the whole data set, you take a big step in that direction, and you go through your training data points one at a time, and all the ones you classified well at that particular iteration, you downweigh their weights for the next time, and the ones you were poor, you upweigh their weights. So it's called adaptive because of the step size automatically is like adapting to the error you incurred at each iteration. So punchline, it wants to increasingly find the parts of the data space where the algorithm is which is hard to learn, and increase the weights on those parts as you go along. So later on, you focus more on the harder parts, and the easy parts you learn sort of in the beginning. So that's sort of roughly explaining the algorithm. So why was boosting sort of such a big deal? Because when these algorithms were introduced, people started observing these phenomena, which are very common these days in the context of neural networks and many other over-parameterized situations. So this is a plot from one of these boosting papers where I'm showing you AdaBoost is being run on some data set. And what I'm showing you here is the curve here is the training error. The curve here is the generalization error. So you see what is now commonly known as the interpolation phenomenon. That is, the training error drops to 0 at stage 5, but the generalization error continues to drop way beyond that. Okay, so you perfectly feed the training data, but your generalization error is continuing to improve. So naturally, that is counterintuitive for us in terms of, it basically doesn't match classical intuition in a lot of contexts. So that piqued the interest of many people, and there was, people were trying to find an explanation for this, and several proposals emerged. And one of these proposals is due to Shapir et al., who said that a key quantity behind the performance of boosting is what they call the empirical margin distribution. So I'm going to explain that. Now, in this classification context, the margin is the following thing. So if I have any classifier f for a training data point, this product yi times f of xi is called the margin of that data point. All right. Now, if you look at the empirical margin distribution, that is, you're looking at, take any threshold and look at fraction of examples for which this product is below that threshold. So you will see a plot like this. Let me explain this plot. So on the x-axis, I have a bunch of numbers between minus, so everything is normalized to be between -1 and 1. So these are my thresholds. And corresponding to each point on the x-axis, on the y-axis, what we are plotting is fraction of training data examples below that corresponding threshold. Okay. Now I have 3 curves here. This corresponds to t equals 5, t equals 100, t equals 1000. Okay. So let's look at t equals 5. So when the when the number of iterations is 5, that's like we are about here, you see that there are many training examples for which the threshold is not too large. But now if we go to t equals 100, this is the empirical margin distribution, right? So what you see is this curve. So t equals 100 means, okay, the generalization error is almost stabilized. And you see that the empirical margin distribution also starts to stabilize. What that means is between t equals 100 to t equals 1000, this almost does not change. And the other thing to note is that when you look at these curves, you automatically see that it means a large number of the training data examples, a large fraction of the training data examples actually have quite large margin. So basically, the explanation Shapiro et al. Had put forward is that the key quantity driving this generalization error is this empirical margin distribution, and boosting or AdaBoost basically tries to produce an eventual classifier such that a large fraction of your examples have a large margin. So in this beautiful paper, they also explain why this is an important quantity, in the sense that they argue this margin is a measure of the confidence you have in your predictions. And there's a lot of intuition here behind all this, but I'm sort of skipping that in the interest of time. Now, this is not just a heuristic observation. They really formalized all of this through this seminal result. So in this work, what they showed is the following. So if you take, let's say, linear classifiers of this form scaled by their L1 norm, this is simplified from their paper. And if you look at the generalization error, you can upper bound it by the following quantity. So let's look at the first quantity. The first quantity is basically the fraction of examples below this threshold kappa. Now, here kappa is any positive number. Okay, so this is a free parameter. And in the other parts, we have n, number of samples, with p, the dimension of the data, and all these things, and you have kappa square here. But the nice thing is, because this kappa is a free parameter, you could optimize this upper bound to basically drive this term to 0, right? Like this term you can try to drive to 0. And one choice you can use to drive this to 0 is the following. So if you choose kappa to be what is called this max min L1 margin. So let's look at this quantity. This is minimum over your all sample points of these margin values given this particular classifier. And then you're taking the worst case of this for all possible theta and RP. Okay, so this quantity is called the max min L1 margin. Now, because I took the minimum here, the moment I plug in this kappa L1 in this first term, this term actually becomes 0. So roughly what I get is the generalization error is less than equals 1 over square root n times this max min L1 margin, okay, from their bounds. Now, the thing is, this is one way to drive this term to 0. And as you can imagine, there could be others too, like this is a free parameter, right? So there seemed to have been a debate that is sort of qualitatively or conceptually, which quantity is really the inherent quantity that's driving the generalization error or boosting. It could be the empirical margin. It could be the max min L1 margin. But because, this is an upper bound, you don't really know. And there was some discussion in this paper on this point where the authors had said that if you really need to close this bound or get tighter bounds, you will need to involve the measurement of more sophisticated statistics. Okay. Okay, so that was sort of one understanding of the generalization behavior in the past. And these bounds were actually later significantly improved by Kolchinsky, Panchenko, Lozano, but still there were upper bounds. So now let's look at the optimization property of AdaBoost. So going back to these works due to Freund and Shapire and Zhang and Yu, another thing that you can show is the following. This display is a bit notation heavy, so maybe let me only present part of it. So this is basically a fraction of examples which were not, number of examples not classified okay. So that you can bound above by terms like this. So let's not look at everything. Let's look at this term gamma t square, okay? Now, gamma t square has a specific form, but if we do some massaging to that, it turns out that we can actually relate that once again to the max min L1 margin. So we can lower bound the absolute value of this by the max min L1 margin. So instead of going over this display, let me present sort of the outcome from all of this. That is, if you were looking at this AdaBoost algorithm, then if you were looking at the number of steps or the number of iterations it takes for the algorithm to interpolate the data or reach zero training error, number of optimization steps, you can actually upper bound that by 1 over square of this max min L1 margin. And there are other log factors and constants, okay? So you see this max min L1 margin, it showed up in the context of generalization, and now it also shows up in the context of the optimization speed of the algorithm. So once again, this just follows from this earlier classical results, but at the same time, this is once again an upper bound. And so I only presented sort of 2 perspectives, and there are many other perspectives in the context of boosting. I mean, this list is by no means exhaustive. There are sort of many other really wonderful works. These margin bounds have been contested by other people. You know, people have looked at consistency properties of the algorithm. There is this entire line of work going back to works of Friedman, then Friedman has Titip-Shirani, which tries to look at boosting as a way of minimizing, you know, empirical loss functionals, fitting stage-wise additive logistic models. And there are also works on boosting in high-dimensional settings, but these works basically focus on L2 boosting, which is a different algorithm than the AdaBoost, okay? I'm happy to talk about, you know, any of this after the talk further, but there are many other perspectives. Okay, and now to conclude the literature review, what I'll conclude with is another insight, which is sort of a very crucial algorithmic insight. So let me introduce these quantities called min L1 norm interpolants, okay? I already said that let's focus on a binary classification setting. And in these settings, what happens is that you can have a lot of scenarios in which your data is linearly separable. So if you look at the 2 classes, if there's a hyperplane passing through, if there's a hyperplane that can separate the 2 classes, we say that the data is linearly separable. Now, if you consider linearly separable data, and then if you look at all possible, you know, vectors that could separate your data in this sense using these linear classifiers. And then if you take the one with the minimum L1 norm among all of these, that's called the min L1 norm interpolated classifier or min L1 norm interpolant, okay? Now, why is this important in the context of boosting? That's because in these works due to Rosette et al. In 2004, Zhang and Yu 2005, what the authors uncovered is actually a very interesting algorithmic property of AdaBoost. So what they showed is that if your data is linearly separable, if you're considering the boosting iterates, then so if you send the step size, so remember sort of we had a step size component in the algorithm. If you send the step size to 0 and if you send the iteration time to infinity, then the boosting iterates converge to the min L1 norm interpolating direction. So when I say direction, I mean these scaled by L1 norms, okay? So That's interesting because previously we saw that the max-min L1 margin was important for describing boosting properties like the generalization, optimization performance. Those were upper bounded by functions of that margin. But now the authors, in some sense, are trying to give you an exact characterization, but under specific kinds of limits. But this is insightful because it kind of says that, okay, if these are under specific kinds of limits, but if you could prove maybe a bit stronger result without these specific limits, maybe there is hope to show that boosting iterates actually converge to this min L1 norm in interpolating direction. And this is interesting because this interpolent is actually the solution to this max min L1 margin problem. So if you solve this problem for theta, the theta that's going to solve it, that's going to be an interpolent for you. Okay. So what do all of these suggest? So far, whatever I've sort of reviewed suggests that it seems that this min L1 norm interpolent and the max min L1 margin, it suggests that these are important players in understanding exact properties of AdaBoost. But in the prior works, you can see that there's some gap that you have upper bounds before, and here you have an exact sort of a characterization, but under a specific limiting sense. So this is sort of where we come in. The questions we're going to ask today are the following. So we are going to be interested to study this L1 margin. So we're going to ask, okay, exactly how large is the L1 margin? Then we're going to ask, okay, what does this min norm interpolent look like? I'll make it precise what look like means. And then we're going to try to understand, okay, can we understand properties of AdaBoost in a bit more refined way? So we're going to try to understand how long does AdaBoost take to reach this min norm interpolating direction. We are going to try to characterize the generalization error of the algorithm precisely. And we're actually also going to try and look at optimization speed of the algorithm. But the hope is AdaBoost is very used, like boosting algorithms in general are, they're used in high dimensional contexts quite a bit. But the hope is here that we are able to provide answers to all of this in some high dimensional setting that can approximate finite sample behavior well. I have another pointer here or within parentheses, which is not there in my slides today, but I should say that we are going to try to do this in a very precise way, but there's no free lunch, okay? So in all the prior works, the assumptions on the data generating distribution were really mild, but there was a gap in the bounds, like these bounds are not tight. So we'll work under specific data generating distribution assumption. And then later we'll try to investigate, okay, how robust is our theory going to be to these assumptions. So I usually have within parentheses that there is no free lunch. Okay, so before I get into the main results, any questions?
Oh, I don't see any questions in chat, and I think you're very clear, so thank you.
Yeah,
oh, there's a question, Wojtek?
I would like to add the question. Yes, because I am not sure, because usually there are something like classifiers which are trained at each iteration. So in your task, these classifiers are just linear classifiers. Am I right? Or
yeah. So currently we are working with that. Yeah, we are working with that kind of simplification. Yeah, but yeah. Sorry, go ahead.
So at each iteration, you choose one variable, I mean, one predictor, and
yeah, one direction like that. But that's also a version of AdaBoost that has been studied a lot in the literature. It's not a very restrictive version. There is an understanding in these works. These are pretty general. So what you'll see is we'll actually characterize this min L1 norm interpolants and go to AdaBoost using that. So all versions of AdaBoost where you have this kind of a result that it's kind of can be approximated by the min L1 norm interpolate. So our results will apply to all those versions of AdaBoost.
Okay.
Thanks for the clarification. Yeah. Okay. So now I'll get into the main results. But before I describe our results, I would like to sort of say which works were sort of our theoretical motivation or technical motivation. So the technique we are going to use in this work is from the literature on Gaussian comparison inequalities. But there is a specific version of the inequalities due to Gordon that is applicable for certain convex problems with a min-max type of form that's known as convex Gaussian min-max theorem. And this was something that started to, started to appear in works due to Stoic around 2013, but sort of the works which really made this precise and really proved it in this version is due to Thrompoulidis et al. Around 2015. So these are our inspirations in terms of, Gaussian comparison stuff. And the other thing I want to mention is we are studying max L1 margin or max min L1 margin, but the max min L2 margin has been significantly studied in the literature and actually by many different communities. It has been studied in the statistical physics community, starting from works due to Gardner in '88, and then Sherbina and Terozzi, and more recently Montanari et al. And then Deng et al. They studied this max min L2 margin using this convex Gaussian min-max theorem tools. But the main difference, so like studying the ridge and studying the lasso are not exactly the same things. Like there are many things it becomes hard to prove for the lasso because of the L1 geometry. So we run into similar problems here. So the L1 and L2 geometries differ significantly. And think of a penalized regression model with the L2 penalization that's going to be strongly convex for broad class of parametric exponential families. But L1 lacks these kinds of nice properties that the L2 has. So that's why sort of even after a lot of work in this context, we have going to L1 calls for novel techniques, and it actually requires new uniform convergence arguments. Okay. So now I'm in a position to get into sort of the technical details. We're going to work in a high dimensional setting. And the setting we'll work with is the following. We'll assume that the number of samples, number of features are both diverging at a fixed ratio in the sense that the limit p by n goes to some positive constant. And this constant can be larger than 1. Okay, so that captures high dimensional data sets. Now, because I have this kind of high dimensional asymptotic regime, I need to formalize the framework a bit more, right? So then we need to assume that we have a sequence of problems, okay, xi, yi, and some theta star, such that what we assume is the distribution, like, okay, so probability that yi equals 1 given xi, this can be modeled through some function f, and then we have xi transpose theta star here. So this is like the logistic model, but f can be a general link function here. Pretty much all the common binary response GLMs you can think of, we can allow all of those links here. The restrictive condition we have is the assumptions on the covariate distribution. So for now, I'm going to assume that they're a Gaussian with mean 0 and have a covariance matrix, but that's diagonal. And yes, I agree that's restrictive, and we'll look at possible generalizations towards the end. But for now, let's assume this structure. And now, okay, so far I have not assumed anything on this sequence of signal vectors. Okay, and so you can imagine that when p is larger than n, I can't really work with such an unstructured problem, right? So what we need is certain regularity conditions. They're sort of relatively general. So the first thing we need is, if you look at the signal strength for this problem, so lambda to the half theta star is basically the L2 norm of this is the signal strength for this problem. So one assumption you need is that in the limit you have a finite signal strength. Okay, rho bigger than 0 is kind of technical condition. We can discuss that later, but we have that for now. But main thing, signal strength is finite in the limit. And there is some other structure that we need. So if I take basically this particular object and on the inside, and I look at its sort of coordinates properly normalized, then I need that lambda j is the eigenvalues of capital lambda, okay? So we need that basically these empirical distributions. So what am I doing here? Capital lambda, it's a deterministic sequence of matrices. And Wj, the W vector, it's also a deterministic sequence of vectors because theta star is deterministic. So each time I take this vector of eigenvalues and I take this vector W, I look at the joint empirical distribution. So this object is putting mass 1 over P on each of these points. So these are 2-dimensional points. Then that has some weak limit. Okay, so it has some weak limit and has some moment convergence. So this part is really a technical condition. If you sit down and work with it, you will see that you can allow different kinds of signals here. Like you can allow certain kinds of sparse signals, you can allow certain kinds of dense signals. Because I'm not assuming sparsity stripe structure at the onset, we do need one regularity condition of this form. So what it says is, okay, these things can't fluctuate too much in magnitude. Like you can't have, you know, for some n, there's one coordinate of theta star, which is very large. For the next, it's like very, you know, you can't have like 2 arbitrary things happening. So this is not that strong in that sense. And the reason why I spent some time on this slide is because the important thing under these high dimensional asymptotics is really trying to crystallize what are the key parameters of the problem. And the key parameters here are these 3 things. So this ratio P by N, this is important. This is psi. This signal strength, this is important. This is rho. And whatever is this limiting distribution, which basically captures how the signal vector and the covariance matrix sequence evolves, that's also important. So these are our 3 problem parameters. And that's something you should take away from the slide. Okay, so this entire high dimensional asymptotic framework, I'm abstracting away by sort of 2 scalar quantities and 1 probability distribution. Okay. All right. Now, we are going to work on, we're going to work on what I call linearly separable data. And from prior work in the literature, we actually have a very good understanding that in a binary classification problem under this high dimensional asymptotic regime, when is the data linearly separable? So let me quickly describe this result. So in an earlier work, which was first posted on arXiv in 2018 by myself and Emmanuel, we had shown that if you're in a logistic regression model, then there is a explicit phase transition curve you can quantify in this psi and rho space, such that below the curve, when I say MLE exists, it is equivalent to saying that the data is not linearly separable. And above the curve, the MLE does not exist, which is equivalent to saying the data is linearly separable. And when I say this, I mean in this asymptotic sense. So here with probability 1, the data is linearly separable. And we had explicit formula for this curve and everything. And it turns out that it's not specific to the logistic regression model. You'll have a very similar formula, even if for general link functions. This was really formalized and worked out in the subsequent Montanari et al. Paper. So in my thesis, I had sort of worked on this regime, but today's work is going to be about this regime. And what that means is that, so if we restrict to this linearly separable regime, it's equivalent to saying that psi, the P by N ratio, is above some threshold that depends on the signal strength, okay? So I can write this curve like this. But if you look at the numbers, the axis numbers here, then this is not a strong condition for high dimensional data sets. So let's see this particular point. So if P by N is above 0.5, no matter what your signal strength is, the data is always linearly separable, right? So you know, you can imagine that for most high dimensional data sets, P by N is above 0.5, right? So this is not that restrictive a condition to lie in, like to restrict ourselves to lie in this regime. This point is also known as Cover's point because it relates to earlier work by Tom Cover. Okay, so once I have this technicality out of the way, now I can actually describe our results in proper detail. So the first thing we show is the following. When you're above this separability threshold, then the max-min L1 margin converges almost surely to a limit. We can quantify this limit very accurately. So this limiting quantity is basically the first time that a certain function crosses 0 And we can pin down this function explicitly. The interesting thing is, this function is related to the MLE existence phase transition curve. And I'll try to describe that a bit in the next slide. But the important thing is, okay, this is the max-min L1 margin, this is the empirical margin scaled by square root p. And this limit can be described using your problem parameters very accurately. So this is an exact limiting characterization. All right, so this function t, it's continuous and non-decreasing, and it crosses 0 at least once. So kappa star, this object is actually well-defined. It's unique, well-defined whenever we are above the separability threshold. Okay, so in the interest of time, maybe what I'm going to do is I have a description of this limit, but I'm going to skip it for now. I'm happy to come back to this slide later. This description also basically tells you how this limiting quantity is related to the phase transition curve, but I'll skip this for now. So just some numerics. Here, what we're doing is, so we have n equals 400, and in the x-axis we have this overparameterization ratio psi. This is a p by n ratio, and we are calculating two things. So we are calculating the empirical max-min L1 margin. So this we can calculate by running linear programming, and we are calculating the limit from our theory. They are color coded. And you can see that even for a few hundred sample sizes, this asymptotic theory gives a very good description of the limiting behavior. These points are almost matching spot on. That's one of the nice things about working in this p by n going to constant regime or proportional asymptotics regime. That is, the theory you get out of there is usually a very good description of finite sample performance for even relatively small sample sizes. And this is not just me observing this or us observing this. This has been observed again and again across varied works in the literature. So that was about the max-min L1 margin. Now, what is it about? Okay, so there's the other quantity, the interpolant, that I had introduced at the beginning. So what we're trying to characterize its generalization error here. So we can also show that we can basically develop an exact formula for the generalization error of this interpolant. So this is the limiting characterization. So let's parse this a bit. So I have three random variables, y, z1, and z2 here. And the description is the following. So y and z1 are independent of z2. The zi's are Gaussian, standard Gaussian. And how do I describe the joint distribution of y and z1? Conditional on z1, this y is almost mimicking our actual response variable in the data. Okay, so let me try to explain this more. So rho is the signal strength in my problem. Z1 is this particular vector. What effectively happens is, let's think of a single data point in my model. So I had a response vector and I had this Gaussian vector, covariate vector, right? Now, because it was Gaussian, I can actually rotate things in a way such that I can put all of the signal in the first coordinate of the covariate vector. And that way my response will be linked to the first coordinate and it will become independent of all the other coordinates. Okay, so this is something I can do on this left-hand side, right? I can rotate things so that y depends on only the first coordinate of x and is independent of everything else. But then what happens is, so the capital Y and Z1 is a prototype for your response vector and this dependence with the first coordinate after this rotation. And there is going to be an independent set of Gaussian stuff, right? Independent set of Gaussian stuff independent from these. So Z2 captures that. And this insight comes from assuming Gaussianity, but I'll show you in plots that the result you get out of this actually doesn't really care about Gaussianity. Like, I think as long as you have some Gaussian tails, the result actually is still spot on. But we'll see some plots for that later. But that's why you have a structure like this. Now, I haven't yet told you what these like mysterious C1 star, C2 star are. So let me give you one description of those, but there are insights into that description, which I'll get to in the next slide. So C1 star, C2 star, these are scalars together with a third scalar S star. It can be implicitly described as a unique solution to a very complicated looking system of equations. The system of equations is parameterized by your problem parameters. So it's parameterized by psi, mu, and the limit of the max min L1 margin. So that's how the interpolant depends on the margin. But okay, the description of the system looks very complex, but numerically you can easily solve it. But the important thing is, this is not really the physical interpretation of these constants. So, the theory tells you it's a solution to a nonlinear system of equations, but there is much more that's actually going on here. So let me try to give you a physical interpretation of these constants. Okay, so what did I show in the previous slide? That the generalization error can be described as follows. The way you can describe these constants is the following. So the C1 star basically captures the angle between your min L1 norm interpolant and the true direction after you do an appropriate change of coordinates using your diagonal matrix. So this inner product is basically theta hat transpose lambda theta star. That's what it is. And the norms here mean like theta hat L1 transpose lambda theta hat L1. Okay. So basically the C1 is capturing this angle between these two vectors, and C2 is essentially capturing the norm of the residual after projection. Going back here, remember that heuristic, I had said I can rotate the x's to put all the signal in the first coordinate. Then if you think about it, to do it correctly, I will also need to project theta hat L1 in the direction of the true theta star. And then I'll have an plus, whatever is the, projection in the orthogonal direction. I'll have something like this. So C1 star captures those constants, the parts coming from theta hat L1. So this is the contribution of, looking at the angle between this and the true direction, but you have to account for the covariance matrix here. And C2 star captures basically whatever is the norm of the residual after your projection. So those are the physical interpretations. Just to show, because I said that, okay, these can be found as solutions to a system of equations. The system looks very nasty. I don't wish to really bother you about that. I have not written the system full form here either. It's more complicated than sort of many of the other problems that have been studied previously in this setting. But let's look at just the main takeaway here. So on the right, I have these expectations over a random variable, over a triplet, over a random vector like this. Now on the right-hand side, for all the three equations, I have this function h, which I have not written out. But the reason why I'm sort of showing this is because this function h is important in the sense that we can actually characterize many other properties of this min L1 norm interpolant using this function h. So basically, if you take any separable function f naught, any function, okay, any convex f naught, and then take these averages. So I have, sorry, this is not theta naught, this is theta star, right? This is true direction. And I take stuff like this. So what can I do? I can plug in, I can take f naught of xy to be x minus y square. So that will give me the norm square difference between the interpolant and the truth, appropriately scaled. So we can characterize those limits precisely. There is more you can do with this result, but that's sort of a digression. But basically, the interpolant in the limit is like whatever this function h is after appropriate scaling. Okay. I didn't talk about this third variable that has been floating around. This basically comes up due to, this corresponds to Lagrange variables corresponding to an L1 norm constraint. But okay, let's keep that for now. Once again, this is a numerics showing an illustration for the generalization error. Again, n equals 400. And the blue points are the empirical generalization error. We can calculate the min L1 norm interpolant by using optimization stuff, and then we know what the theory tells us. So you see the points match pretty well, but you do see that at the beginning the points don't match as well. And that's important to note because our theory only tells you what the limit on linearly separable data, and that's true only for psi above some threshold. So you shouldn't trust these first 3 points. Our theory is not for these 3 points. So you should really look at the curve like later on here. Okay, so I had gone off on this entire trajectory on like min L1 norm interpolant and max min L1 margin. So now let's come back to boosting. How does this help us understand AdaBoost properties? So the thing we're able to show is the following. With the proper choice of non-vanishing step size, the non-vanishing is important here because in the past, there was an understanding which was using infinitesimal step size. So with the proper choice of non-vanishing step size, if you look at the sequence of AdaBoost iterates, they have the following properties. So there is a stopping time we can characterize such that for all time points above the stopping time, for all iteration times above the stopping time, if you look at the minimum margin L1 in this sense across your training data points using the boosting solution, scale it properly, then that's arbitrarily close to the limit of your max min L1 margin. Okay, so I can choose epsilon whichever way I please. And using this, actually, you can connect the generalization error of boosting. You can come up with an accurate description of generalization error of AdaBoost, because this means this is going to be arbitrarily close to the min L1 norm interpolant. And for those, we understand the generalization behavior accurately from what I presented before. And now let's look at the stopping time. So we can show that, okay, with an appropriate scaling that will involve the sample size, this has a precise limit, and we know the limit exactly, okay? And then we can investigate this limit to figure out what is the optimization speed of the algorithm. So we're going to do that. All right, trying to compare with the classical generalization error bound. So this was the classical bound or a consequence of the classical bound. I can rewrite things in the asymptotic regime we are in, and then the bound looks like this. So here, this orange curve is basically this particular classical bound, and our limiting theory tells us that the generalization error lies somewhere here. So they kind of asymptote. And then trying to understand the stopping time better. So what we can do is we can plot, let's plot this denominator as a function of psi, okay? So what we see here is as the overparameterization ratio increases, this denominator increases, so this object decreases. And what does that mean? So the moment you hit this time point, after that, our theory says with this step sizes, after that, the generalization error stabilizes, right? So basically, as psi increases, you optimize faster. And what's the rough intuition behind this? So the rough intuition is, as a problem gets more overparameterized, you know, the landscape becomes maybe more complicated, and you might end up having a lot of min-norm interpolants in that case. And then, so, you know, when you start from a certain initialization, you can basically reach one of these interpolants easily. So the optimization speed increases. We are not aware of a formalization of this intuition in the boosting context. This is a sort of general intuition that's there in the neural nets literature too. And people have tried to formalize it in various ways, but there's like, this is one way to formalize it in the context of AdaBoost. All right, so I think I'm close to the time limit. Gaussian, how much time do I have?
Let's say that we are pretty much relaxed with time. So usually the seminar is like 1 hour, but you can take a bit longer. So it will be still like 10 minutes of regular time, and maybe a little more if you would like to stay longer.
Okay, sure. Yeah, so far I was talking about AdaBoost, and we studied this min L1 norm interpolance, max min L1 margin. And remember my slide, which was trying to say that technically going from L2 to L1, there is a hurdle which is induced by the L1 geometry. But while proving the things for the L1 stuff, what we essentially needed to prove was some intrinsic properties of the phase transition curve. So this is totally counterintuitive why, just this was enough. So we needed to prove some intrinsic properties of the phase transition curve. Now, the phase transition curve is really about the data properties. It's not about which margin or which interpolant you use. So that curve was really, when is the data linearly separable, right? So the nice thing about this was that whatever we did for L1 can easily generalize to any other LP, okay? Now, in the context, in the boosting literature, there have been prior work suggesting that, okay, if there's high dimensional data, it's not really clear if you should do AdaBoost, if you're going for an AdaBoost type algorithm, should you do AdaBoost, or should you do a version of AdaBoost which converges to min LQ interpolating, to the min LQ interpolating direction? So you can generalize the AdaBoost algorithm very naturally and easily to look at, to come up with an algorithm which corresponds to the min LQ norm interpolating direction. I've just written the algorithm slightly differently here, but just changing. So for AdaBoost, this will be L1 norm equals 1. So you can do this naturally. You can write this algorithm out naturally. But because L2 to L1 was a jump, but the way we did it for L1 helps us and generalize to other LQ easily. So we can characterize max min LQ margin in a very analogous way. The scaling is going to change, and the form of the limit is going to change, but the inherent description remains the same. So we can analogously write out this nonlinear system of equations, and we can characterize the result on the interpolant. We can characterize the corresponding result for this version of boosting with this new system of equations. And all the geometric insights that I said about look at the angle, look at the norm of the residual, they all go through. Just the exact form of the system of equations, the exact description of those constants changes. But qualitatively or conceptually, everything else remains the same. Okay, so quick glimpse maybe into the proof sketch. There's some notation in the slides, but I'm trying to maybe do away with the notations while describing and just talk about the key points. So the goal is to study a problem of this form, it's max min L1 margin, right? Now, with some massaging, you can show that studying this problem is actually equivalent to studying this min-max optimization problem. So forget how the objective function looks like. It's important, but it's important in the next stage, not right now. Here, what you should see is, okay, this is over theta in L1 ball less than equals some square root p, and this is over this kind of an L2 ball, and you have non-negative. So there are two parameters you're optimizing over. Now, this convex Gaussian minimax theorem I had talked about, that's a very nice result in the Gaussian comparison inequalities literature, which says the following. So if you have an optimization problem of this form, min max over two variables w1, w2, and if it is in this quadratic form plus some function where Z is a matrix with IID Gaussian entries, all right, and U is convex concave in W1, W2 respectively. And what is important is these sets omega 1 and omega 2, they are both compact. Okay. So then you can basically, and you have some convexity requirements too on the set. So then you can basically decouple this Z into two vectors, two Gaussian vectors. So you can rewrite this quadratic form in terms of norm of W2, G transpose W1, and norm of W1, H transpose W2. Okay, where G and H are two vectors now, IID Gaussian. So effectively what it's doing is, okay, this is a hard problem because of this quadratic form, you're decoupling and having this in this vector form. So this becomes a simpler problem. So any min-max objective like this, I can always use this version as long as I have an IID Gaussian matrix here. So I get a decoupled version of our problem. That's where we use this machinery. However, then you have to study this decoupled version, and that's always problem specific. So it doesn't mean that you applied this hammer that necessarily studying this simpler problem is kind of easy in your case. So then you have to characterize the limit of this particular decoupled optimization problem. So, okay, it looks quite nasty. Let's not look at that. But the important thing I want to mention is I just wanted to show the difference between L2 and L1 geometry. So I can write this decoupled problem using, so I can call this term C1, let's say this term C2. And when you're looking at the max min L2 margin, what happens is your constraint set here is that norm of theta 2 is less than equals 1. Okay. But that means this C2 term, you have a bound on that C2 term because this is L2 norm of this object and it has a theta in there. However, now the constraint is an L1 norm constraint here, and there is a square root p here. So this C2 actually can be unbounded, the second term. So that creates a lot of problems. So I just wanted to mention the difference between, sorry, I don't know why my mouse is just super sensitive. Come on. Yeah, so that creates, technical difficulties. And just to see, we had 3 equations, right? And 3 variables. So 2 of the variables are coming up from these 2 arguments. And the third one is coming up from, if I write out the KKT condition for this optimization problem, you will have Lagrange variables corresponding to these constraints. And that's where our third variable comes up from. So you get 3 equations here. All right, so we described all of this under sort of restrictive assumptions on the covariate matrix. So let's look at what happens if you don't have Gaussianity in your covariate matrix, okay? So again, the x-axis here, it's psi over parameterization ratio. The y-axis on the left, what I'm doing is I'm plotting max min L1 margin. For the blue ones, those correspond to a Gaussian design, and the orange ones correspond to a ±1 design with certain probability. So it's different from the Gaussian, but it has nice sub-Gaussian tails, and pretty much nothing really changes between these settings. And these kinds of, these new kinds of numerics have been observed in this context for other problems in these kinds of high-dimensional asymptotic regime. And in a lot of cases, universality actually has been proved. In some cases, it has been proved that whatever you get for Gaussian, you get the same thing for sub-Gaussian designs. So we haven't proved that in the context of this problem yet, but I think that's something, there is hope to be able to do something there. The simulations are strongly convincing in that context. In some sense, the harder problem is when you start introducing correlations in the design, then the thing starts to change. So here what I'm doing is I'm restricting to Gaussian design, but I am basically looking at AR designs and I'm changing the autocorrelation magnitude. Now, what you see is the trend remains the same, okay? But the exact, behavior, so we are plotting max min L1 margin on the left-hand side. The exact behavior of the margin starts changing. So there is work to be done here in, trying to understand, okay, how can we change our description of those limits so that it can naturally, capture these correlated settings. But there have been recent works in this context for other problems. One of them by myself and Sean and Emmanuel, and then more recently by Celentano Montanari Way, where people have started tackling correlations in these problems. And, this particular problem doesn't fall in the category of either of those. So there is much work to be done here, but, there is hope that, okay, something should be doable, but not something we have proved yet. But there are other kinds of covariates where we've been able to extend, and there's work by Trampoulidis et al. In the L2 margin case, where also they have looked at those kinds of models, which are sort of Gaussian mixture models. So these are nice. If you have a Gaussian mixture model of this form, so sorry, there's no comma here, yi times theta star plus zi, yi is ±1. Then if I look at yi given, like there is some correlation in the xi's in that case, right? But these kinds of situations we can actually handle, even if we have finitely many other directions here. These are situations we can handle. So that's like some extension into correlations in covariates. Okay, so I'm going to wrap up now. So what I presented was precise characterization of this max min L1 margin, min L1 norm interpolant, and that gives us several insights into AdaBoost. I write boosting in some cases, but I was talking about AdaBoost. There are some other results we had which I didn't cover. We have some more geometric insights, which tries to capture, okay, how many coordinates of the AdaBoost algorithm are active when it first interpolates the training data. So AdaBoost, there's hope that it produces kind of a sparse solution. So trying to understand this kind of question is sort of interesting. Like, is it basically producing a sparse solution or a dense solution? And we have extensions to certain misspecified models. One takeaway is the results doesn't rely too much on the geometry. So we can cover LQ for Q bigger than 1. And so you can compare between these different interpolants using our formula. We had characterization of prediction error. So that's something to look at, because in the whole neural networks area, like there are some insights that maybe looking at LQ interpolants might be better for some Q other than 1 or 2. So this work can provide sort of the first guiding principles in like comparing between these interpolants. And I mean, this opens door to further questions, which I'm happy to talk about. Of course, like this is the big problem of understanding AdaBoost is that's far from being solved. Okay, thank you. And I mean, okay, you can find the paper on my webpage on AdaBoost. I didn't write the name here, but yeah. Thank you so much for your attention.